the students for live session today, and today we are going to handle the physics complete chapters related to Karnataka board and CBSE syllabus, and the classes commences now, and please try to note down the important points, and it will be very useful for your examinations. Yeah, Bhavana Manasa has entered the session. Welcome all. And you're going to watch the videos and try to note down the important points. That will be very helpful for your examination. Okay? Don't miss. Try to note down the important points and try to watch completely all the videos without fail.
Introduction. It is widely used form of energy. Introduction. It is widely used form of energy. Main examples of its usage are lighting, heating, refrigeration, air conditioning, pumping water, working on computers, charging mobile phones, television, etc. Flow of charges through a conductor is electricity. When a circuit is completed, we see it in action. When we switch on, fan starts to rotate. This completes the circuit. This flow of charges is measured in units of current, that is, rate of flow of charges over a particular area with specified time is called electric current. Generally, it is the flow of electrons that provides electric current. The direction of movement of positive charges is considered as the direction of flow of current, that is, the opposite direction of flow of electrons. Definitions: electric current and electric circuit. Electric current. The flow of electric charge is known as electric current. Electric current is carried by moving electrons through a conductor. By convention, electric current flows in opposite direction to the movement of electrons. Electric circuit. Electric circuit is a continuous and closed path of electric current. Expression of electric current. Electric current is denoted by letter I. Electric current is expressed by the rate of flow of electric charges. Rate of flow means the amount of charge flowing through a particular area in unit time. If a net electric charge Q flows through a cross-section of conductor in time t, then electric current I equal to net charge Q by time t, or I equal to Q by t, where I is electric current, Q is net charge, and t is time in second. SI unit of electric charge and current. SI unit of electric charge is coulomb, C. 1 coulomb is nearly equal to 6 into 10 raised to 18 electrons. SI unit of electric current is ampere, A. The unit ampere is named after a French scientist, André-Marie Ampere. Ampere is the flow of electric charges through a surface at the rate of 1 coulomb per second. This means if 1 coulomb of electric charge flows through a cross-section for 1 second, it would be equal to 1 ampere. Therefore, 1 amps equal to 1 coulomb per second. Small quantity of electric current. Small quantity of electric current is expressed in milliampere and microampere. Milliampere is written as MA and microampere as MUA. 1 milliampere equal to 10 raised to minus 3 amps. 1 microampere equal to 10 raised to minus 6 amps. Ammeter, an apparatus to measure electric current in a circuit. Example 1. Find the amount of electric charge flowing through the circuit if an electric charge of 5 amps is drawn by an electric appliance for 5 minutes. Solution given electric current I equal to 5 amps, time t equal to 5 minutes equal to 5 into 60, that is equal to 300 seconds. Electric charge Q to be found out. We know I equal to Q by T, or Q equal to I into T, or Q equal to 5 amps into 300 seconds equal to 1500 coulombs. Example 2. If a current of 2 ampere is drawn for 1 hour through the filament of a bulb, find the amount of electric charge flowing through the circuit. Solution given electric current I equal to 2 amps, time t equal to 1 hour, that is equal to 1 into 60 into 60 seconds equal to 3600 seconds. Electric charge Q to be found out. We know that Q equal to I into T. Therefore, Q equal to 2A into 3600 seconds, that is equal to 7200 coulombs. Example 3. In how much time 6000 coulombs of electric charge will flow if an electric current of 10 amps is drawn through an electric motor? Solution given electric charge Q equal to 6000 coulombs, electric current I equal to 10 amps, time t equal to unknown. We know I equal to Q by T, or T equal to Q by I, or T equal to 6000 coulombs divided by 10 amps equal to 600 seconds, or T equal to 10 minutes. Example 4. If an electric charge of 900 coulombs flows through an electric bulb for half an hour, find the electric current drawn by the filament. Solution given electric charge Q equal to 900 coulombs, time t equal to half an hour, that is equal to 30 minutes, that is equal to 30 into 60, that is equal to 1800 seconds. Electric current I to be found out. We know I equal to Q by T, or I equal to 900 coulombs divided by 1800 seconds, that is equal to 0.5 amps. Example 5. If an electric charge of 1500 coulombs flows through an electric iron for 5 minutes, find the electric current drawn by filament of electric iron. Solution given electric charge Q equal to 1500 coulombs, time t equal to 5 minutes, that is equal to 5 into 60, that is equal to 300 seconds. Electric current I to be found out. We know I equal to Q by T, for I equal to 1500 coulombs divided by 300 seconds equal to 5 amps. Electric potential and potential difference. What makes charge flow? Just like flow of water from higher level to lower level, electric charge also flows from higher potential to lower potential. This potential difference can be created by a battery. It pumps the charges from its storage to make current flow in the circuit. Electric potential. The amount of electric potential energy at a point is called electric potential. Electric potential difference. The difference in the amount of electric potential energy between 2 points in an electric circuit is called electric potential difference. Electric potential difference is known as voltage, which is equal to the work done per unit charge to move the charge between 2 points against static electric field. Therefore, voltage equal to work done by charge. Voltage or electric potential difference is denoted by V. Therefore, V equal to W by Q, equation 1, where W equal to work done and Q equal to charge. SI unit of electric potential difference, voltage. SI unit of electric potential difference is volt and denoted by letter V. This is named in honor of Italian physicist Alessandro Volta. V equal to Joule by Coulomb, that is equal to J by C, or V equal to J into C raised to minus 1. Since Joule is the unit of work and Coulomb is the unit of charge, 1 volt of electric potential difference is equal to 1 joule of work to be done to move a charge of 1 coulomb from one point to another in an electric circuit. Therefore, 1 volt equal to 1 joule by 1 coulomb, that is equal to 1 J by 1 C, or 1 V equal to 1 into Jc raised to minus 1. Voltmeter, an apparatus to measure the potential difference or electric potential difference between 2 points in an electric circuit. Example 1. Calculate the work done if a charge of 5 coulombs moving across 2 points having potential difference equal to 15 volts. Solution given potential difference V equal to 15 volts, charge Q equal to 5 coulombs. Work done W to be found out. We know that V equal to W by Q, or W equal to V into Q, or W equal to 15 volts into 15 coulombs equal to 75 joules. Example 2. Calculate the work done to carry a charge of 3 coulombs if the potential difference between 2 points is 10 volts. Solution given charge equal to 3 coulombs, potential difference between 2 points equal to 10 volts. Work done W to be found out. We know that V equal to W by Q, or W equal to V into Q, or W equal to 10 volts into 3 coulombs, that is equal to 30 joules. Example 3. What potential difference is required to do 100 joules of work to carry a charge of 10 coulombs between 2 points? Solution given work done W equal to 100 joules, charge Q equal to 10 coulombs. Potential difference V to be found out. We know that V equal to W by Q, or V equal to 100 joules divided by 10 coulombs equal to 10 volts. Example 4. Calculate the potential difference between 2 points if 1500 joules of work is done to carry a charge of 50 coulombs from one point to other. Solution given work done W equal to 1500 joules, charge Q equal to 50 coulombs. Potential difference V to be found out. We know that V equal to W by Q, or V equal to 1500 joules divided by 50 coulombs equal to 30 volts. Example 5. 5000 joules of work would be done to carry how much charge between 2 points having potential difference of 100 volts. Solution given potential difference V equal to 100 volts. Work done W equal to 5000 joules. Charge Q to be found out. We know that V equal to W by Q, or Q equal to W by V, or Q equal to 5000 joules divided by 100 volts, that is equal to 50 coulombs. Example 6. To carry how much charge between 2 points having potential difference equal to 220 volts, 1760 joules of work is done. Solution given potential difference V equal to 220 volts. Work done W equal to 1760 joules. Charge Q to be found out. We know that V equal to W by Q, or Q equal to W by V, or Q equal to 1760 joules divided by 220 volts is equal to 8 coulombs. Ohm's law. Ohm's law states that the potential difference between 2 points is directly proportional to the electric current. This means potential difference V varies as electric current, or V is directly proportional to I. V by I equal to R, equation 1. 1 by I equal to R by V, that gives I equal to V by R, equation 2. Therefore, V equal to Ri, equation 3, where R is constant for the given conductor at a given temperature and is called resistance. Resistance is the property of conductor which resists the flow of electric current through it. SI unit of resistance is ohm. Ohm is denoted by Greek letter. 1 ohm of resistance R is equal to the flow of 1 amps of current through a conductor between 2 points having potential difference equal to 1 volt. This means 1 ohm equal to 1 volt by 1 amps. From the expression of Ohm's law, it is obvious that electric current through a resistor is inversely proportional to resistance. This means electric current will decrease with increase in resistance and vice versa. The graph of V, potential difference, versus I, electric current, is always a straight line. Example 1. Calculate the resistance if 5 amps of electric current flows through a conductor having potential difference between 2 points that is equal to 15 volts. Solution. Given electric current I equal to 5 amps, potential difference V equal to 15 volts. Resistance R to be found out. We know from Ohm's law that R equal to V by I. Therefore, R equal to 15 volts by 5 amps. Therefore, R equal to 3 ohms. Example 2. If the potential difference between the terminals of an electric motor is 220 volts and an electric current of 5 amps is flowing through it, what will be the resistance of electric motor? Solution. Given electric current I equal to 5 amps, potential difference V equal to 220 volts, resistance R to be found out. We know from Ohm's law that R equal to V by I. Therefore, R equal to 220 volts by 5 amps. Therefore, R equal to 44 ohms. Example 3. An electric current of 15 amps is flowing through an electric fan. If the potential difference between 2 terminals of electric fan is 240 volts, what will be the resistance? Solution. Given electric current I equal to 15 amps, potential difference V equal to 240 volts. Resistance R to be found out. We know from Ohm's law that R equal to V by I. Therefore, R equal to 240 volts by 15 amps. Therefore, R equal to 16 ohms. Example 4. If the resistance of an electric iron is 48 ohms and an electric current of 5 amps is flowing through it, what will be the potential difference between 2 terminals of an electric iron? Solution. Given electric current I equal to 5 amps, resistance R equal to 48 ohms, potential difference V to be found out. We know from the Ohm's law that R equal to V by I. 48 ohms equal to V by 5 amps. 48 ohms into 5 amps equal to V. Therefore, V equal to 240 volts. Example 5. Calculate the potential difference between 2 points of a terminal if an electric current of 10 amps is flowing through it, having resistance of 20 ohms. Solution. Given electric current I equal to 10 amps, resistance R equal to 20 ohms, potential difference V to be found out. We know from Ohm's law that R equal to V by I. Therefore, 20 ohms equal to V by 10 amps. Therefore, 20 ohms into 10 amps equal to V. Therefore, V equal to 200 volts. Example 6. If the resistance between 2 terminals of an electric heater is 15 ohms and an electric current of 15 amps is flowing through it, then what will be the voltage of electric current? Given electric current I equal to 15 amps, resistance R equal to 15 ohms, voltage, that is potential difference V to be found out. We know from Ohm's law that R equal to V by I. Therefore, 15 ohms equal to V by 15 amps. 15 ohms into 15 amps equal to volt. Therefore, V equal to 225 volts. Resistance. Resistance is a property of conductor due to which it resists the flow of electric current through it. Component that is used to resist the flow of electric current in a circuit is called resistor. In practical applications, resistors are used to increase or decrease the electric current. Variable resistance. The component of an electric circuit which is used to regulate the current without changing the voltage from the source is called variable resistance. Rheostat. This is a device which is used in a circuit to provide variable resistance. Cause of resistance in a conductor. Flow of electrons in a conductor is electric current. The particles of conductor create hindrance to flow of electrons because of attraction between them. This hindrance is the cause of resistance in the flow of electricity. Resistance in a conductor depends on nature, length, and area of cross-section of the conductor. Nature of material. Some materials create least hindrance and hence are called good conductors. Silver is the best conductor of electricity, while some other materials create more hindrance in the flow of electric current, that is, flow of electrons through them. Such materials are called bad conductors. Bad conductors are also known as insulators. Hard plastic is one of the best insulators of electricity. Length of conductor. Resistance R is directly proportional to the length of the conductor. This means resistance increases with increase in length of the conductor. This is the cause that long electric wires create more resistance to the electric current. Thus, resistance R is proportional to the length of conductor L, or R is proportional to L. Equation 1. Area of cross-section. Resistance R is inversely proportional to the area of cross-section A of the conductor. This means R will decrease with increase in the area of conductor and vice versa. More area of conductor facilitates the flow of electric current through more area and thus decreases the resistance. This is the cause that thick copper wire creates less resistance to the electric current. Thus, resistance is proportional to 1 by area of cross-section of conductor A, or R is proportional to 1 by A, equation 2. From equation 1 and 2, R is proportional to L by A. Therefore, R equal to rho L by A, equation 3, where rho is the proportionality constant. It is called the electrical resistivity of the material of conductors. From equation 3, Ra equal to rho L, rho equal to Ra by L, equation 4. The SI unit of resistivity. Since the SI unit of R is ohm, SI unit of area is meter square, and SI unit of length is meter. Hence, unit of resistivity rho equal to ohm into meter square by meter equal to ohm meter. Thus, SI unit of resistivity rho is ohm meter. Materials having resistivity in the range of 10 raised to minus 8 ohm meter to 10 raised to minus 6 ohm meter are considered as very good conductors. Silver has resistivity equal to 1.60 into 10 raised to minus 8 ohm meter, and copper has resistivity equal to 1.62 into 10 raised to minus 8 ohm meter. Rubber and glass are very good insulators. They have resistivity in the order of 10 raised to 12 ohm meter to 10 raised to 17 ohm meter. Resistivity of materials varies with temperature. Example 1. What will be the resistivity of a metal wire of 2 meter length and 0.6 millimeter in diameter if the resistance of the wire is 50 ohms? Solution given resistance R equal to 50 ohms, length L equal to 2 meter, diameter equal to 0.6 millimeter. Hence, radius equal to 0.3 millimeter equal to 3 into 10 raised to minus 4 meter. Resistivity rho to be found out. Now, area of cross section of wire equal to pi r square, or A equal to 3.14 into within the brackets 3 into 10 raised to minus 4 whole square, or A equal to 28.26 into 10 raised to minus 8 meter square. That is equal to 2.826 into 10 raised to minus 9 meter square. We know that rho equal to Ra by L. Therefore, rho equal to 50 ohm into 2.826 into 10 raised to minus 9 meter square by 2m. Rho equal to 25 into 2.826 into 10 raised to minus 9 ohm meter. That is equal to 70.65 into 10 raised to minus 9 ohm meter. Therefore, rho equal to 7.065 into 10 raised to minus 8 ohm meter. Example 2. The resistance of an electric wire of an alloy is 10 ohms. If the thickness of wire is 0.001 meter and length is 1 meter, find its resistivity. Solution: given resistance R equal to 10 ohms, length L equal to 1 meter, diameter equal to 0.001 meter. Therefore, radius equal to 0.0005 meter. Resistivity rho to be found out. Now, area of cross section of wire equal to pi r square, or A equal to 3.14 into 0.005 whole square meter square, or A equal to 0.00007850 meter square. We know that rho equal to RA by L. Therefore, rho equal to 10 ohms into 0.0000785 meter square by 1 n. Therefore, rho equal to 10 ohms into 0.0000785 meter. Therefore, rho equal to 0.000785 ohm meter. That is equal to 7.85 into 10 raised to minus 4 ohm meter. Example 3. The resistivity of a metal wire is 10 into 10 raised to minus 8 ohm meter at 20 degrees Celsius. Find the resistance of the same wire of 2 meter length and 0.3 millimeter thickness. Solution: given resistivity ohm equal to 10 into 10 raised to minus 8 ohm meter, length L equal to 2 meter, diameter equal to 0.3 millimeter. Resistance R to be found out. Now, radius of wire equal to diameter by 2, that is equal to 0.3 millimeter by 2 equal to 0.15 millimeter, that is equal to 1.5 into 10 raised to minus 5 meter. Now, area of cross section of wire equal to pi r square, or A equal to 3.14 into brackets open 1.5 into 10 raised to minus 5 whole square, or A equal to 70.65 into 10 raised to minus 10 meter square. We know that R equal to rho L by A. R equal to 10 into 10 raised to minus 8 ohm meter into 2 meter by 7.65 into 10 raised to minus 9 meter square. Therefore, R equal to 10 into 2 ohms by 7.65 into 10. That is equal to 2 ohms by 7.65. That is equal to 0.26 ohm. Example 4. The area of cross section of wire becomes half when its length is stretched to double. How resistance of wire is affected in this new condition? Solution: let the area of cross section of wire be A. Let length of wire before stretching be L. Let resistance of wire be R. After stretching of wire, let area of cross section be A by 2. Length equal to 2L, resistance equal to R1. Thus, ratio of resistance before stretching to resistance after stretching can be given as follows. R is to R1 equal to rho L by A is to rho 2L by A by 2. Therefore, R is to R1 equal to rho L by A is to 4 rho L by A. Therefore, R is to R1 equal to 1 is to 4. This means R equal to 1 and R1 equal to 4. Thus, resistance increases 4 times after stretching of wire. Resistors in series and parallel. Resistors are joined in two ways, that is, in series and in parallel. Resistors in series. When resistors are joined from end to end, it is called in series. In this case, the total resistance of the system is equal to the sum of the resistance of all the three resistors in the system. Let total resistance equal to R. Resistance of resistors are R1, R2, R3, so on up to Rn. Therefore, R equal to R1 plus R2 plus R3 plus so on up to Rn. Resistors in parallel. When resistors are joined in parallel, the reciprocal of total resistance of the system is equal to the sum of reciprocal of the resistance of resistors. let total resistance equal to R. Resistance of resistors are R1, R2, R3, so on up to Rn. 1 by R equal to 1 by R1 plus 1 by R2 plus 1 by R3 plus so on up to 1 by Rn. Example 1. There are 3 resistors joined in series in a system having resistance equal to 10 ohms, 20 ohms and 30 ohms respectively. If the potential difference of the circuit is 240 volts, find the total resistance and current to the circuit. Solution: given R1 equal to 10 ohms, R2 equal to 20 ohms, R3 equal to 30 ohms and V equal to 240 volts. Total resistance R to be found out. Current through the circuit I to be found out. According to Ohm's law of total resistance in series, R equal to sum of resistance of all resistors, or R equal to 10 ohms plus 20 ohms plus 30 ohms equal to 60 ohms. We know that electric current I equal to V by R, or I equal to 240 volts divided by 60 ohms equal to 4 amps. Thus, total resistance R equal to 60 ohms. Current through the circuit equal to 4 amps. Example 2. There are 2 electric lamps M and N which are joined in a series having resistance equal to 15 ohms and 20 ohms respectively. If the potential difference between 2 terminals of electric circuit is 220 volts, find the total resistance and electric current through the circuit. Also, find the potential difference across the 2 lamps separately. Solution: given resistance R1 of 1 electric lamp M equal to 15.2 ohms. Resistance R2 of other electric lamp N equal to 20 ohms. Potential difference V through the circuit equal to 220 volts. Electric current I through the circuit to be found out. Potential difference through each of the electric lamp to be found out. According to Ohm's law, total resistance in series equal to sum of resistance of all resistors equal to 15.2 ohms plus 20 ohms equal to 35.2 ohms. Electric current I equal to V by R equal to 220 volts divided by 35.2 ohms equal to 6.25 amps. Potential difference V1 across electric lamp N equal to 15.2 ohms divided by 6.25 amps, that is equal to 2.432 volts. Potential difference V2 across electric lamp N equal to 20 ohms divided by 6.25 amps equal to 3.2 volts. Thus, electric current through the circuit equal to 6.25 amps. Potential difference through electric lamp N equal to 2.432 volts. Potential difference through electric lamp N equal to 3.2 volts. Example 3. There are 2 resistors R1 and R2 having resistance equal to 20 ohms and 30 ohms respectively are connected in parallel in an electric circuit. If the potential difference across the electric circuit is 5 volts, find the electric current flowing through the circuit and the total resistance of the resistors. Solution: given R1 equal to 20 ohms, R2 equal to 30 ohms, potential difference V equal to 5 volts. Total resistance R to be found out, electric current I through the circuit to be found out. We know that in parallel combination, the reciprocal of total resistance is 1 by R equal to 1 by R1 plus 1 by R2. Therefore, 1 by R equal to 1 by 20 ohms plus 1 by 30 ohms. That is equal to 3 plus 2 by 60 ohms equal to 5 by 60 ohms. That is equal to 1 by 12 ohms. Now, electric current through the circuit I equal to V by R, or I equal to 5 volts divided by 12 ohms equal to 0.416 amps. Thus, total resistance R equal to 12 ohms. Electric current I through the circuit equal to 0.416 amps. Example 4. There are 5 electric appliances, namely electric heater and electric lamp, an electric fan, computer, and an exhaust fan are connected in parallel in a household. The resistance electric appliances are 40 ohms, 5 ohms, 8 ohms, 20 ohms, and 10 ohms respectively. If an electric current of 240 volts is flowing through the circuit, then find A. Total resistance through the circuit, B. Total electric current I through the circuit, and C. The current through each of the resistor. Solution. We know that the reciprocal of total resistance equal to sum of reciprocals of individual resistances. 1 by R total equal to 1 by 40 ohms plus 1 by 5 ohms plus 1 by 8 ohms plus 1 by 20 ohms plus 1 by 10 ohms. That is equal to 1 plus 8 plus 5 plus 2 plus 4 by 40 ohms. That is equal to 20 by 40 ohms equal to 1 by 2 ohms, or R total equal to 2 ohms. Now, electric current through the circuit equal to V by R, or I equal to 240 volts divided by 2 ohms equal to 120 amps. Similarly, electric current through different appliances can be calculated as follows. Electric current through heater equal to 240 volts divided by 40 ohms equal to 6 amps. Electric current through electric lamp equal to 240 volts divided by 5 ohms equal to 48 amps. Electric current through electric fan equal to 240 volts divided by 8 ohms equal to 30 amps. Electric current through computer equal to 240 volts divided by 20 ohms equal to 12 amps. Electric current through exhaust equal to 240 volts divided by 10 ohms equal to 24 amps. The total current through the circuit can be calculated by adding the electric current through individual resistors, or I total equal to 6 amps plus 48 amps plus 30 amps plus 12 amps plus 24 amps, that is equal to 120 amps. Heating effect of electric current. When electric current is supplied to a purely resistive conductor, the energy of electric current is dissipated entirely in the form of heat, and as a result, resistor gets heated. The heating of resistor because of dissipation of electric energy is commonly known as heating effect of electric current. Some examples are as follows. When electric energy is supplied to an electric bulb, the filament gets heated because of which it gives light. The heating of electric bulb happens because of heating effect of electric current. When an electric iron is connected to an electric circuit, the element of electric iron gets heated because of dissipation of electric energy, which heats the electric iron. The element of electric iron is a purely resistive conductor. This happens because of heating effect of electric current. Cause of heating effect of electric current. Electric current generates heat to overcome the resistance offered by the conductor through which it passes. Higher the resistance, the electric current will generate higher amount of heat. Thus, generation of heat by electric current while passing through a conductor is an inevitable consequence. This heating effect is used in many appliances such as electric iron, electric heater, electric geyser, etc. Joule's law of heating. Let an electric current I is flowing through a resistor having resistance equal to R. The potential difference through the resistor is equal to V. The charge Q flows through the circuit for the time t. Thus, work done in moving of charge Q of potential difference V equal to V by Q. Since the charge Q flows through the circuit for time t, therefore, power input P to the circuit can be given by the following equation. P equal to V into Q by T. Equation 1. We know electric current I equal to Q by T. Substituting Q by T equal to I in equation 1, we get P equal to VI, equation 2. Since the electric energy is supplied for time t, thus after multiplying both sides of equation 2 by time t, we get P into T equal to VI into T equal to VIT. Thus, for steady current I, the heat produced H in time t is equal to VIT, or H equal to VIT, equation 4. We know according to Ohm's law, V equal to IR. By substituting the value of V in equation 4, we get H equal to IR into IT, or H equal to I squared RT, equation 5. The equation 5 is known as Joule's law of heating, which states that heat produced in a resistor is directly proportional to the square of current given to the resistor, directly proportional to the resistance for a given current, and directly proportional to the time for which the current is flowing through the resistor. Example 1. If an electric heater consumes electricity at the rate of 500 watts and the potential difference between the two terminals of electric circuit is 250 volts, calculate the electric current and resistance through the circuit. Solution. Given power input P equal to 500 watts, potential difference V equal to 250 volts, electric current I to be found out, resistance R through the circuit to be found out. We know that power P equal to VI, or 500 watts equal to 250 volts into I, or I equal to 500 watts divided by 250 volts equal to 2 amps. We know resistance R equal to V by I, or R equal to 250 volts divided by 2 amps equal to 125 ohms. Example 2. An electric geyser consumes electricity at the rate of 1000 watts. If the potential difference through the electric circuit is 250 volts, find the resistance offered by geyser and electric current through the circuit. Solution. Given power input P equal to 1000 watts, potential difference V equal to 250 volts, electric current I to be found out, resistance R to the circuit to be found out. We know that power P equal to VI, or 1000 watts equal to 250 volts into I, or I equal to 1000 watts divided by 250 volts, that is equal to 4 amps. We know resistance R equal to V by I, or R equal to 250 volts divided by 4 amps equal to 62.5 ohms. 62.5 ohms. Example 3. An electric heater having resistance equal to 5 ohms is connected to electric source. If it produces 180 joules of heat in 1 second, find the potential difference across the electric heater. Solution. Given resistance R equal to 5 ohms, heat H produced per second by heater equal to 180 joules, time t equal to 1 second. Potential difference V to be found out. To calculate the potential difference, we need to calculate electric current I first. We know that H equal to I squared RT, or 180 joules equal to I squared into 5 ohms into 1 second, or I squared equal to 180 divided by 5 equal to 36, or I equal to 6 amps. Now, potential difference V equal to IR, or V equal to 6 amps into 5 ohms equal to 30 volts. Heating effect application. Practical application of heating effect of electric current and electric power. For exploiting the heat effect of electric current, the element of appliances must have high melting point to retain more heat. The heating effect of electric current is used in the following applications. Electric bulb. In an electric bulb, the filament of bulb gives light because of heating effect of electricity. The filament of bulb is generally made of tungsten metal having melting point equal to 3380 degrees Celsius. Electric iron. The element of electric iron is made of ions having high melting point. Electric heater and geyser work on the same mechanism. Electric fuse. Electric fuse is used to protect the electric appliances from high voltage if any. Electric fuse is made of metal or alloy of metals such as aluminum, copper, iron, lead, etc. In the case of flow of higher voltage than specified, fuse wire melts and protects the electric appliances. Fuse of 1 amp 2 amps, 3 amps, 5 amps, 10 amps, etc. are used for domestic purpose. Suppose if an electric heater consumes 1000 watts or 220 volts, then electric current in circuit I equal to P. I equal to 1000 watts divided by 220 volts, that is equal to 4.5 amps. Thus, in this case, a fuse of 5 amps should be used to protect the electric heater in the case of flow of higher voltage. Electric power. SI unit of electric power is watt. W. 1 watt equal to 1 volt into 1 ampere, that is equal to 1 volt into 1 amps. 1 kilowatt or 1 kW equal to 1000 watts. Consumption of electricity, electric energy is generally measured in kilowatt. Unit of electric energy is kilowatt per hour. 1 kilowatt per hour equal to 1000 watt into 1 hour, that is equal to 1000 watts into 3600 seconds. Or 1 kilowatt per hour equal to 3.6 into 10 raised to 6 watt second, that is equal to 3.6 into 10 raised to 6 joules. Example 1. If the potential difference is 220 volts and the power of bulb is 110 watts, what is the electric current flowing in the circuit? Solution. Given potential difference V equal to 220 volts, power of bulb P equal to 110 watts. Electric current I to be found out. We know that P equal to VI, or 110 watts equal to 220 volts into I, or I equal to 110 watts divided by 220 volts equal to 0.5 amps. Example 2. If the power of an electric heater is 1000 watts and electricity of 240 volts is flowing through it, find the electric current in the electric heater. Solution. Given power P equal to 1000 watts, potential difference V equal to 240 volts, electric current I to be found out. We know that P equal to VI, or 1000 watt equal to 240 volts into I, or I equal to 1000 watts divided by 240 volts is equal to 4.6 amps. Example 3. What is the electric current to an electric geyser of 500 watts? If the potential difference across the electric circuit is 250 volts. Solution. Given P equal to 500 watts, V equal to 250 volts, therefore electric current I to be found out. We know that P equal to VI, or 500 watts equal to 250 volts into I, or I equal to 500 watts divided by 250 volts equal to 2 amps. Example 4. If the electric current is 10 amps and the potential difference between two terminals is 240 volts, find the power of the electric appliance. Solution. Given electric current I equal to 10 amps, potential difference V equal to 240 volts, power P to be found out. Since P equal to V into I, therefore P equal to 240 volts into 10 amps equal to 2400 watts. Example 5. Find the power of electric iron in electric current through the circuit is 5 amps and the potential difference is 220 volts. Solution. Given electric current I equal to 5 amps, potential difference V equal to 220 volts, power P to be found out. We know that P equal to V into I, or P equal to 220 volts into 5 amps, that is equal to 1100 watts. Electricity at a glance. Electric current. The flow of electric charge is known as electric current. Electric current is carried by moving electrons through a conductor. Electric current flows in the opposite direction of the movement of electrons. Electric circuit. Electric circuit is a continuous and closed path of electric current. Electric current is denoted by letter I. Electric current is expressed by the rate of flow of electric charges, that is, amount of charge flowing through a particular area in unit time. SI unit of electric charge is coulomb. C. 1 coulomb is nearly equal to 6 into 10 raised to 18 electrons. SI unit of electric current is ampere. A. Ampere is the flow of electric charges through a surface at the rate of 1 coulomb per second. 1 milliampere equal to 10 raised to minus 3 amps and 1 MUA or microampere equal to 10 raised to minus 6 amps. Ammeter, an apparatus to measure electric current in a circuit. Electric potential. The amount of electric potential energy at a point is called electric potential. Electric potential difference. The difference in the amount of electric potential energy between 2 points in an electric circuit is called electric potential difference. Electric potential difference is known as voltage, which is equal to the work done per unit charge to move the charge between 2 points against static electric field. It is denoted by V. Voltmeter, an apparatus to measure the potential difference or electric potential difference between 2 points in an electric circuit. Ohm's law. The potential difference between 2 points is directly proportional to the electric current. SI unit of resistance is ohm. Ohm is denoted by Greek letter. 1 ohm of resistance R is equal to the flow of 1 amps of current through a conductor between 2 points having potential difference equal to 1 volt. Component that is used to resist the flow of electric current in a circuit is called resistor. Variable resistance. The component of an electric circuit which is used to regulate the current without changing the voltage of the source is called variable resistance. Rheostat. This is a device which is used in a circuit to provide variable resistance. Resistance in a conductor depends on nature, length, and area of cross-section of the conductor. Resistance increases with increase in length of the conductor. Resistance decreases with increase in thickness of conductor. Resistors in series. When resistors are joined from end to end, it is called in series. The total resistance of the system is equal to the sum of the resistance of all the resistors connected in series in the system. Resistors in parallel. Where resistors are joined in parallel, the reciprocal of total resistance of the system is equal to the sum of reciprocal of the resistance of resistors. When electric current is supplied to a purely resistive conductor, the energy of electric current is dissipated entirely in the form of heat, and as a result, resistor gets heated. The heating of resistor because of dissipation of electrical energy is commonly known as heating effect of electric current. Joule's law of heating. Heat produced in a resistor is directly proportional to the square of current given to the resistor, directly proportional to the square of current given to the resistor, directly proportional to the resistance for a given current, and directly proportional to the time for which the current is flowing through the resistor. SI unit of electric power is watt, W. 1 watt equal to 1 volt into 1 ampere, that is equal to 1 volt into 1 amp. 1 kilowatt or 1 kW equal to 1000 watts. 1 kilowatt per hour equal to 1000 watts into 1 hour, that is equal to 1000 watts into 3600 seconds. Therefore, 1 kilowatt per hour equal to 3.6 into 10 raised to 6 watts second, that is equal to 3.6 into 10 raised to 6 joules.
Okay, this completes the chapter electricity. Now we'll move on to the next chapter. Magnetic effects of electric current. Try to note down the points without missing.
Chapter 13. Magnetic effects of electric current. Introduction. Properties of magnet. A free suspended magnet always points towards north and south direction. The pole of a magnet which points toward north direction is called north pole or north seeking. The pole of a magnet which points towards south direction is called south pole or south seeking. Like poles of magnets repel each other, while unlike poles of magnets attract each other. Similar to other effects, electric current also produces magnetic effect. The magnetic effect of electric current is known as electromagnetic effect. It is observed that when a compass is brought near a current carrying conductor, the needle of compass gets deflected because of flow of electricity. This shows that electric current produces a magnetic effect, magnetic field and field lines. The influence of force surrounding a magnet is called magnetic field. In the magnetic field, the force exerted by a magnet can be detected using a compass or any other magnet. The imaginary lines of magnetic field around a magnet are called field line or field line of magnet. When iron films are allowed to settle around a bar magnet, they get arranged in a pattern which mimics the magnetic field lines. Field line of a magnet can also be detected using a compass. Magnetic field is a vector quantity, that is, it has both direction and magnitude. Direction of field line. Outside the magnet, the direction of magnetic field line is taken from North Pole to South Pole. Inside the magnet, the direction of magnetic field line is taken from South Pole to North Pole. Strength of magnetic field. The closeness of field lines shows the relative strength of magnetic field. That is, closer lines show stronger magnetic field and vice versa. Crowded field lines near the poles of magnet show more strength. Magnetic field due to current carrying conductor. Magnetic field due to current through a straight conductor. A current carrying straight conductor has magnetic field in the form of concentric circles around it. Magnetic field of current carrying straight conductor can be shown by magnetic field lines. The direction of magnetic field through a current carrying conductor depends upon the direction of flow of electric current. The direction of magnetic field gets reversed in case of a change in the direction of electric current. Let a current carrying conductor be suspended vertically and the electric current is flowing from south to north. In this case, the direction of magnetic field will be anti-clockwise. If the current is flowing from north to south, the direction of magnetic field will be clockwise. Right hand thumb rule, current, magnetic field. The direction of magnetic field in relation to direction of electric current through a straight conductor can be depicted by using the right hand thumb rule. It is also known as Maxwell's Corkscrew rule. If a current carrying conductor is held by right hand, keeping the thumb straight, and if the direction of electric current is the direction of thumb, then the direction of wrapping of other fingers will show the direction of magnetic field. As per Maxwell's Corkscrew rule, if the direction of forward movement of screw shows the direction of current, then the direction of rotation of screw shows the direction of magnetic field. Properties of magnetic field. The magnitude of magnetic field increases with increase in electric current and decreases with decrease in electric current. The magnitude of magnetic field produced by electric current decreases with increase in distance and vice versa. The size of concentric circles of magnetic field lines increases with distance from the conductor, which shows that magnetic field decreases with distance. Magnetic field lines are always parallel to each other. No two field lines cross each other. Magnetic field due to current through a circular loop. In case of a circular current carrying conductor, the magnetic field is produced in the same manner as it is in case of a straight current carrying conductor. In case of a circular current carrying conductor, the magnetic field lines would be in the form of concentric circles around every part of the periphery of the conductor. Since magnetic field lines tend to remain closer when near the conductor, so the magnetic field would be stronger near the periphery of the loop. On the other hand, the magnetic field lines will be distant from each other when we move towards the center of the current carrying loop. Finally, at the center, the arcs of big circles would appear or as a straight line. The direction of magnetic field can be identified using right hand thumb's rule. Let us assume that the current is moving in anti-clockwise direction of the loop. In that case, the magnetic field would be in clockwise direction at the top of the loop. Moreover, it would be in anti-clockwise direction at the top of the loop. Clock phase rule. A current carrying loop works like a disk magnet. The popularity of this magnet can be easily understood with the help of clock phase rule. If the current is flown in anti-clockwise direction, then the phase of the loop shows north pole. On the other hand, if the current is flown in clockwise direction, then the phase of the loop shows south pole. Magnetic field and number of turns of coil. Magnitude of magnetic field gets summed up with increase in number of turns of coil. If there are n turns of coil, magnitude of magnetic field will be n times of magnetic field in case of a single turn of coil. Magnetic field due to a current in a solenoid. Solenoid is a coil with many circular turns of insulated copper wire wrapped closely in the shape of cylinder. A current-carrying solenoid produces similar pattern of magnetic field as a bar magnet. One end of solenoid behaves as the north pole and another end behaves as the south pole. Magnetic field lines are parallel inside the solenoid, similar to a bar magnet, which shows that magnetic field is as same at all points inside the solenoid. By producing a strong magnetic field inside the solenoid, magnetic materials can be magnetized. Magnet formed by producing magnetic field inside a solenoid is called electromagnet. Force on current-carrying conductor in magnetic field. A current-carrying conductor exerts a force when a magnet is placed in its vicinity. Similarly, a magnet also exerts equal and opposite force on the current-carrying conductor. This was suggested by Ampere, a French physicist and considered as founder of science of electromagnetism. The direction of force over the conductor gets reversed with a change in direction of flow of electric current. It is observed that the magnitude of force is highest when the direction of current is at right angles to the magnetic field. Fleming's left-hand rule. If direction of electric current is perpendicular to the magnetic field, the direction of force is also perpendicular to both of them. The Fleming's left-hand rule states that if the left hand is stretched in a way that the index finger, the middle finger, and the thumb are in mutually perpendicular directions, then the index finger and the middle finger of a stretched left hand show the direction of magnetic field and direction of electric current respectively, and the thumb shows the direction of motion of force acting on the conductor. The directions of electric current, magnetic field, and force are similar to three mutually perpendicular axes, that is, x, y, and z axes. Many devices such as electric motor, electric generator, loudspeaker, etc. works on the Fleming's left-hand rule. Electric motor. Electrical energy is converted into mechanical energy by using an electric motor. Electric motor works on the basis of rule suggested by Ampere and Fleming's left-hand rule. In an electric motor, a rectangular coil is suspended between the two poles of a magnetic field. The electric supply to the coil is connected with a commutator. Commutator is a device which reverses the direction of flow of electric current through a circuit. When electric current is suspended to the coil of electric motor, it gets deflected because of magnetic field. As it reaches the halfway, the split ring which acts as commutator reverses the direction of flow of electric current. Reversal of direction of current reverses the direction of forces acting on the coil. The change in direction of force pushes the coil and it moves another half turn. Thus, the coil completes one rotation around the axle. Continuation of this process keeps the motor in rotation. In commercial motor, electromagnet instead of permanent magnet, an armature is used. Armature is a soft iron core with large number of conducting wire turns over it. Large number of turns of conducting wire enhances the magnetic field produced by armature. Electromagnetic induction. Microparading, an English physicist, is supposed to have studied the generation of electric current using magnetic field and a conductor. When a conductor is said to move inside a magnetic field or a magnetic field is said to be changing around the conductor, electric current is induced in the conductor. This is just opposite to the exertion of force by a current carrying conductor inside a magnetic field. In other words, when a conductor is brought in relative motion while with a magnetic field, a potential difference is induced in it. This is known as electromagnetic induction. Electromagnetic induction can be explained with the help of Fleming's right-hand rule. If the right hand is stretched in a way that the index finger, middle finger, and thumb are in mutually perpendicular directions, then the thumb shows the direction of movement of the conductor. Index fingers shows the direction of magnetic field, and the middle finger shows the direction of induced current in the conductor. The directions of movement of conductor, magnetic field, and induced current can be compared to three mutually perpendicular axes, that is, x, y, and z axis. The mutually perpendicular directions also point to an important fact that when the magnetic field and movement of conductor are perpendicular, the magnitude of induced current will be maximum. Electromagnetic induction is used in the conversion of kinetic energy into electrical energy. Electric generator. The structure of electric generator is similar to that of an electric motor. In case of an electric generator, a rectangular armature is placed within the magnetic field of a permanent magnet. The armature is attached to wire and is positioned in a way that it can move around an axle. When the armature moves within the magnetic field, an electric current is induced. The direction of induced current changes when the armature crosses the halfway mark of its rotation. Thus, the direction of current changes once in every rotation. Due to this, the electric generator usually produces alternate current, that is AC. To convert an AC generator into a DC generator, a split ring commutator is used. This helps in producing direct current. AC and DC current. AC, alternate current. Current in which direction is changed periodically is called alternate current. In India, most of the power stations generate alternate current. The direction of current changes after every 1/100 seconds in India. That is, the frequency of AC in India is 500 Hz. AC is transmitted up to a long distance without much loss of energy is advantage of AC over DC. DC, direct current, current that flows in one direction only, is called direct current. Electrochemical cells produces direct current.
Okay, this completes the magnetic effects chapter, and we'll move on to the next chapter. Sources of energy.
Chapter 14, Sources of Energy. Introduction. When we use energy in its usable form, we convert the form of energy and get our work done during the process. Since we cannot reverse the change involved in this process, we cannot get back the original usable form of energy. Due to this, it becomes important to think about energy shortage and the related energy crisis. Characteristics of a good source of energy. It should be able to do large amount of work for each unit of mass or volume. It should be easily accessible. It should be easily transported. It should be economical. Conventional sources of energy. The sources of energy which have been in use since a long time are called conventional sources of energy. Coal, petroleum, natural gas, hydel energy, wind energy, and nuclear energy are considered to be the conventional sources of energy. Additionally, firewood is also a conventional source of energy, but its usage is now limited to kitchens in the rural parts of India. Fossil fuels. Coal. Coal was formed millions of years ago. The plants got buried under swamps, and due to high pressure and high temperature inside the earth, they were converted into coal. Coal is the highest used energy source in India. During the days of steam engine, coal was used in steam engines. Moreover, coal was also used as kitchen fuel before LPG became popular. Nowadays, coal is mainly being used in the industries. Petroleum. Petroleum was also formed millions of years ago. The animals got buried under the ocean surface and were converted into petroleum in due course of time. Petroleum is the third major source of energy being used today. Petroleum products are used as automobile fuel and also in the industries. Natural gas mainly comes from the oil wells and is also a major source of energy. Non-renewable sources of energy. It takes millions of years for the formation of fossil fuels. Since they cannot be replenished in the foreseeable future, they are known as non-renewable sources of energy. Renewable sources of energy. Those sources of energy which can be replenished quickly are called renewable sources of energy. Hydel energy, wind energy, and solar energy are examples of renewable sources of energy. Hydel energy. Hydel energy is produced by utilizing the kinetic energy of flowing water. Huge dams are built over a source of water. Water is collected behind the dam and released. When the water falls on the turbine moves because of kinetic energy of water. Thus, electricity is generated by the turbine. Electricity thus generated is called hydel energy or hydroelectricity. Water in the reservoir is replenished with rainwater, and so availability of water is not a problem for hydroelectricity. Drawbacks of hydel plant. Building large dams is not good for the ecosystem. When a large dam is built, a vast tract of land in its vicinity gets submerged. This destroys a large part of the vegetation and wildlife, which does immense damage to the ecosystem. Moreover, when the submerged vegetation decomposes it, produces a huge amount of methane gas. Methane is a potential greenhouse gas and thus is not good for the environment. Building large dam also affects a huge section of population which lives in the surrounding areas. Many villages need to be evacuated. Although the government comes with some rehabilitation plan for them, but the displacement of people from their roots has its own costs involved. Thermal power plant. In a thermal power plant, coal or petroleum is used for converting water into steam. The steam is used to run the turbine to generate electricity. Biomass. The plants and animals constitute the biomass. Firewood from plants is used as kitchen fuel. If large number of trees can be planted, then a continuous supply of firewood can be ensured. Farm waste such as stalks of harvested plants and dung of cattle can be used to generate methane. The decomposition of biomass produces methane which can be channelized for useful purposes. Biogas plant. Biogas plants can be very useful in solving the energy need of rural areas. A biogas plant is a dome-like structure which is usually built from bricks and concrete. In the mixing tank, the slurry is made from cow dung and water. The slurry then goes to the digester, which is a closed chamber. Since oxygen is absent in the digester, the anaerobes carry on their work for decomposition. The process of decomposition produces biogas. Biogas has about 70% of methane and the rest is composed of other gases. The biogas is channelized through a pipe and can be utilized as kitchen fuel and also as fuel for getting light. The slurry left behind is removed and it is used as manure once it dries. Wind energy has been in use since ages. The sailboats of the pre-industrialization era used to run on wind power. Windmills have been in use especially in Holland since the medieval period. Nowadays, windmills are being used to generate electricity. The kinetic energy of wind is utilized to run the turbines which generate electricity. At present, Germany is the leading country in terms of wind energy production and India comes at number 5. In India, Tamil Nadu is the largest wind energy producing state. The largest wind farm in India is near Kanyakumari in Tamil Nadu, which generates 380 megawatts of electricity. Limitations of wind energy. Wind farms can only be established at those places where the wind speed is high enough and is more than 15 km per hour for most parts of the year. Wind farms need to be established on large tracts of land. The fan of the windmill has many moving parts, so cost of maintenance and repair is quite high. The fact that it has to suffer the vagaries of the nature further compounds the problem. Initial cost of establishing a wind farm is very high. Non-conventional sources of energy. Energy sources which are relatively new are called non-conventional sources of energy. Example, nuclear power and solar energy. Solar energy. The sun is the main source of energy for all living beings on this earth. Even the energy in the fossil fuels has come from the sun. The sun has an endless reservoir of energy which will be available as long as the solar system is in existence. Technologies for harnessing the solar energy have been developed in recent times. Solar cooker. Solar cooker is very simple in design and mode of function. It is usually made from mirrors. Plain mirrors are placed inside a rectangular box. The light reflected from the plain mirrors concentrates the solar energy inside the solar cooker, which generates enough heat to cook food. Solar furnace. Solar furnace is made like a concave mirror. Large solar furnace has many smaller mirrors to compose a very large convex mirror. The thing to be heated is placed near the focus of the mirror. Solar cells. Solar cells are made from silicon. The solar panel converts solar energy into electrical energy, which is stored in a battery for later use. Energy from sea. Tidal energy. Due to the gravitational pull of the moon, tides happen near seashores. Water rushes up near the seashore during a high tide and goes down during a low tide. Dams are built near seashores to collect the water which comes during a high tide. When the water runs back to the ocean, the flow of water can be utilized to generate electricity. Wave energy. Waves can also be a good source of energy. Many devices are also being designed and tested to produce wave energy. For example, a halo tower is built near the seashore. When water gushes in the tube because of wave, it forces the air upwards. The kinetic energy of air in the tube is used to run a turbine. When the wave goes down, air from up goes down the tube, which is also used in running the turbine. Ocean thermal energy. The water at sea surface is hot during daytime, while the water at lower level is cold. The temperature differential in water levels can be utilized to generate energy. If the temperature differential is more than 20 degrees Celsius, then ocean thermal energy can be utilized from that place. For this, a volatile liquid like ammonia is boiled using the heat from the hot water at the surface. The steam of the volatile liquid is utilized to run the turbine to generate electricity. Colder water from the surface below is utilized to condense ammonia vapor, which is then channelized to the surface to repeat the cycle. Various methods of harnessing energy from the sea are still at experimental stages. Geothermal energy. The molten rocks from the inside of the earth are pushed in certain regions of the earth. Such regions are called the hotspots of the earth. When groundwater comes in contact with such hotspots, lot of steam is generated. This steam can be harnessed to produce energy. Many power plants in New Zealand and USA operate on geothermal energy. Nuclear energy. Nuclear fission is the process during which two nuclei fuse to form one nucleus. The process generates a huge amount of energy. This phenomenon is utilized in nuclear power plants. Nuclear power is safest for the environment, but the risk of damage due to accidental leaks of radiation is pretty high. Further, storage of nuclear waste is a big problem because of potential risk of radiation involved. Nonetheless, many countries are using nuclear power in a big way. India too has built many nuclear power plants. Recent accidents in the nuclear power plants in Chernobyl in Japan have forced the policy makers to rethink about the nuclear power.
Okay, this completes the alternate source of energy, and we have the last lesson. The human eye and the colorful world. This is not for 10th standard students. The people who are studying right now in the 9th, it will be useful for upcoming classes. Okay, this I'll play at the last. Before to that, I'll play once again the chapter Light, which I already played in a previous session.
Chapter 10, Light, Reflection and Refraction. Introduction. Light is a form of energy. It induces sensation of vision to our eyes. As we can see many It travels in straight line. See, it forms shadows. Reflection. Reflection is one of the unique properties of light. It is the reflection of light which enables us to see any object. The bouncing back of rays of light from a polished and shiny surface is called reflection or reflection of light. It is similar to bouncing back of a basketball after colliding with any hard surface. A few important definitions are incident ray, a ray of light that strikes the surface. Reflected ray, a ray of light that is reflected from the surface. Point of incidence, it is the point at which the incident ray strikes the surface. Normal, it is the line drawn at the point of incidence perpendicular to the surface. Angle of incidence. It is angle between normal and incident ray. It is denoted by I. Angle of reflection. It is the angle between normal and reflected ray. It is denoted by R. Laws of reflection of light. The angle of incidence and angle of reflection are equal. The incident ray, reflected ray, and normal to the point of reflection lie in the same plane. The laws of reflection are applicable to all types of reflecting surface, that is, plane and spherical surfaces. Mirror and reflection of light. Mirror is a shiny polished object, glass, which reflects most of the rays of light falling upon it. One side of mirror is polished with suitable material to make the other side reflective. Types of image formed by mirrors. Real image. Image which is formed in front of the mirror and can be obtained on a screen is called real image. Virtual image. Image which is formed behind the mirror and cannot be obtained on a screen is called virtual image. Types of mirror. Plane mirror. A mirror having a flat surface is called plane mirror. Formation of image in plane mirror. Light rays from the object spread and hit the reflecting surface. They appear to come from a point behind the mirror. The image is denoted by I. A plane mirror always forms virtual and erect image. The distance of image and that of object is equal from the mirror. The image formed by a plane mirror is laterally inverted. Lateral inversion. Apparent reversal of the image left and right when compared with the object, that is, the sides of the object are reversed. Right becomes left and left becomes right. This is only in the direction perpendicular to the surface of the mirror. Ambulance word is painted left-right inverted on the vehicle. This will enable the driver of the vehicle ahead to read the word correctly and give way. Properties of images formed by plane mirror are: A. Image is virtual and cannot be projected on screen. B. Image is erect. C. Image of the same size as that of object. D. Laterally inverted. E. Distance of the object and image are same from the mirror. Uses of plane mirror. 1. To look at ourselves. 2. Use in periscope. 3. Decoration purpose in shops. Spherical mirror. Mirrors have curved reflecting surface are called spherical mirrors. A spherical mirror is a part of a sphere. Types of spherical mirror. Concave mirror. Spherical mirror with reflecting surface curved inwards is called concave mirror. Convex mirror. Spherical mirror with reflecting surface curved outwards is called convex mirror. Laws of reflection are applicable to all types of mirrors. Important terms in the case of spherical mirror. Concave mirror. Pole. The center of reflecting surface of a spherical mirror is known as pole. Pole lies in the surface of spherical mirror. Pole is generally represented by P. Center of curvature. The center of sphere of which the reflecting surface of a spherical mirror is a part, and it is called the center of curvature of the spherical mirror. Center of curvature is not a part of spherical mirror, rather it lies outside the mirror. Center of curvature is denoted by letter C. In the case of concave mirror, center of curvature lies in front of the reflecting surface. On the other hand, center of curvature lies behind the reflecting surface in the case of convex mirror. Radius of curvature. The radius of sphere of which the reflecting surface of a spherical mirror is a part, and it is called the radius of curvature of the spherical mirror. The radius of curvature of a spherical mirror is denoted by letter R. Similar to center of curvature, radius of curvature lies in front of concave mirror and lies behind the convex mirror and is not a part of the mirror as it lies outside the mirror. Aperture. The diameter of reflecting surface of a spherical mirror is called aperture. Principal axis. Imaginary line passing through the center of curvature and pole of a spherical mirror is called the principal axis. Focus or principal focus. Point on principal axis at which parallel rays coming from infinity converge after reflection is called the focus or principal focus of the spherical mirror. Focus is represented by letter F. In case of a concave mirror, parallel rays coming from infinity converge after reflection in front of the mirror. Thus, the focus lies in front of a concave mirror. In case of a convex mirror, parallel rays coming from infinity appear to be diverging from behind the mirror. Thus, the focus lies behind the convex mirror. Focal length. The distance from pole to focus is called focal length. Focal length is denoted by letter F. Focal length is equal to half the radius of curvature, or F equal to R by 2, or R equal to 2F. Reflection of rays parallel to principal axis. In the case of concave mirror, a ray parallel to principal axis passes through the principal focus after reflection from a concave mirror. Similarly, all parallel rays to the principal axis pass through the principal focus after reflection from a concave mirror. Since a concave mirror converges the parallel rays after reflection, thus a concave mirror is also known as converging mirror. A concave mirror can be used to focus rays of light. When sunlight is focused on paper, it burns a hole upon it. Heat produced due to the concentration of sunlight burns the paper. This is the focus of the mirror. In the case of convex mirror, a ray parallel to principal axis appears to diverge from the principal focus after reflecting from the surface of a convex mirror. Similarly, all rays parallel to the principal axis of a convex mirror appear to diverge or coming from principal focus after reflection from a convex mirror. Since a convex mirror diverges the parallel rays after reflection, thus it is also known as diverging mirror. Reflection of ray passing through the principal focus. In the case of concave mirror, ray passing through the principal focus goes parallel to principal axis after reflection in the case of concave mirror. In the case of convex mirror, a ray directed towards principal focus goes parallel to principal axis after reflecting from the surface of a convex mirror. Ray passing through the center of curvature. In the case of concave mirror, ray passing through the center of curvature returns at the same path after reflecting from the surface of a concave mirror. In the case of convex mirror, ray appears to be passing through or directed towards the center of curvature, goes parallel to the principal axis after reflecting from the surface of a convex mirror. Ray incident obliquely to the principal axis. Ray obliquely to the principal axis goes obliquely after reflecting from the pole of the both concave and convex mirror and at the same angle. Image formation by concave mirror. Formation of image depends upon the position of the object. There are 6 possibilities of the position of objects in the case of concave mirror. A. Object at infinity. B. Object between infinity and center of curvature. C. Object at center of curvature. C. D. Object between center of curvature C and principal focus F. E. Object at principal focus F. F. Object between principal focus F and pole P. Object at infinity. Since parallel rays coming to the object converge at principal focus F of a concave mirror after reflection. Hence, when the object is at infinity, the image will form at F. Properties of image. Point size, highly diminished, real and inverted. Object between infinity and center of curvature. When object is placed between infinity and center of curvature of a concave mirror, the image is formed between center of curvature C and focus F. Properties of image. Diminished compared to object. Real and inverted. Object at center of curvature C. When the object is placed at center of curvature C of a concave mirror, a real and inverted image is formed at the same position. Properties of image. Same size as object. Real and inverted. Object between center of curvature C and principal focus F. When the object is placed between center of curvature and principal focus of concave mirror, a real image is formed beyond the center of curvature C. Properties of image. Larger than object, real and inverted. Object at principal focus F. When the object is placed at principal focus F of a concave mirror, a highly enlarged image is formed at infinity. Properties of image. Highly enlarged, real and inverted. Object between principal focus F and pole P. When the object is placed between principal focus and pole of a concave mirror, an enlarged virtual and erect image is formed behind the mirror. Properties of image: enlarged, virtual and erect. Positions of object and image in concave mirror. Position of object, position of image, size of image, nature of image. At infinity, at focus, point size highly diminished, real and inverted. Between infinity and C, between F and C, diminished, real and inverted. At C, same size, real and inverted. Between C and F, beyond C, enlarged, real and inverted. At F, at infinity, highly enlarged, real and inverted. Between F and P, behind mirror, enlarged, virtual and erect. Image formation by convex mirror. There are only two possibilities of position of object in case of a convex mirror, that is, object at infinity and object between infinity and pole of a convex mirror. Object at infinity. When the object is at the infinity, a point-sized image is formed at principal focus behind the convex mirror. Properties of image. Image is highly diminished, virtual and erect. Object between infinity and pole. When the object is between infinity and pole of a convex mirror, a diminished, virtual and erect image is formed between pole and focus behind the mirror. Properties of image. Image is diminished, virtual and erect. Positions and nature of image in convex mirror. Position of object, position of image, size of image, nature of image. At infinity. At F, behind the mirror, highly diminished, virtual and erect. Between infinity and P, between F and P, behind mirror, diminished, virtual and erect. Uses of concave and convex mirror. Uses of concave mirror as reflector in electric torch, headlights of vehicle, searchlight, etc. The source of light is put at the focus of the reflector, which produces a strong parallel beam of light, which helps in clear visibility. As shading mirror, to produce larger image of face to facilitate better viewing during shading. Concave mirror is used by dentists to see larger image of teeth of the patient. When a tooth is placed between focus and pole, the concave mirror produces a magnified image of the tooth. As reflector in solar furnace. By using concave mirror in solar furnace, the concentrated rays of sunlight is obtained at focus, which produces enormous amount of heat because of concentration. Uses of convex mirror. Convex mirror is used in rear view mirror of vehicles so that the driver can see the traffic coming from behind. The field of view is widest in case of a convex mirror, which enables it to show a wider area from behind. Convex mirror is used on hairpin bends on the road so that the driver can see the traffic approaching from another side of the bend. Sign convention for spherical mirror. Cartesian sign convention. In the case of spherical mirror, all signs are taken from pole of the spherical mirror, which is often called origin or origin point. This sign convention is known as New Cartesian sign convention. Sign is taken as negative from pole of a spherical mirror towards object along the principal axis. This means sign is always taken as negative, minus, in front of a spherical mirror. For example, the distance of object is always taken as negative, minus, in case of both types of spherical mirror, that is concave and convex mirror. Sign is taken as plus, positive, behind the spherical mirror. For example, if an image is formed behind the mirror, the distance of image is taken as positive from pole along the principal axis. The height of it is taken as plus, positive, above the principal axis and taken as minus, negative, below the principal axis. Sign in the case of concave mirror. Since object is always placed in front of the mirror, hence the sign of object is taken as negative. Since the center of curvature and focus lies in front of concave mirror, So, sign of radius of curvature and focal length are taken as negative in case of concave mirror. When image is formed in front of the mirror, the distance of image is taken as negative, and when image is formed behind the mirror, the distance of image is taken as positive. Height of image is taken as positive in the case of erect image and taken as negative in the case of inverted image. Sign in the case of a convex mirror. Since object is always placed in front of the mirror, hence the sign of object is taken as negative. Since the center of curvature and focus lies behind the convex mirror, so sign of radius of curvature and focal length are taken as positive in the case of convex mirror. In the case of convex mirror, image always forms behind the mirror, thus the distance of image is taken as positive. In the case of a convex mirror, always an erect image is formed, thus the height of image is taken as positive. Mirror formula. Mirror formula shows the relation among distance of object, distance of image, and focal length in case of spherical mirror. All distances are measured from pole of the mirror. The distance of object is denoted by u. The distance of image is denoted by v. Focal length is denoted by f. 1 by v plus 1 by u equal to 1 by f. Mirror formula. By knowing any two, the third can be calculated using the mirror formula. Magnification. Magnification is the relative ratio of size of image formed by a spherical mirror to the size of object. Magnification is generally denoted by letter m. Magnification m equal to height of image h dash by height of object h, or m equal to h dash by h. Relation among magnification, distance of object and distance of image. Magnification n equal to distance of image by distance of object equal to minus v by u. Thus, m equal to h dash by h equal to minus v by u, where m equal to magnification, h dash equal to height of image, h equal to height of object, v equal to image distance, and u equal to object distance. Refraction Introduction. The change of direction of light because of change of medium is known as refraction or refraction of light. The ray of light changes its direction or phenomenon of refraction takes place because of difference in speed in different media. The light travels at faster speed in rare medium and at slower speed in denser medium. The nature of media is taken as related. For example, air is a rarer medium than water or glass. When ray of light enters from a rarer medium into a denser medium, it bends towards normal at the point of incidence. On the contrary, when ray of light enters into a rarer medium, from a denser medium, it bends away from the normal. Ray emerging after the denser medium goes in the same direction and parallel to the incident ray. The angle between incident ray and normal is called angle of incidence, and it is denoted as I. The angle between refracted ray and normal is called the angle of refraction. Angle of refraction is denoted by R. Laws of refraction. The incident ray, refracted ray, and normal to the interface of given two transparent media all lie in the same plane. Ratio of sine of angle of incidence and sine of angle of refraction is always constant for the light of given color and for the pair of given media. Second law of refraction is also known as Snell's law of refraction, that is, sin I by sin R equal to constant. Constant is called refractive index of the second medium in relation to the first medium. Refractive index. A ray of light changes its direction when it enters from one medium to another medium. This happens because speed of light is different in different media. For example, the speed of light is 3 into 10 raised to 8 meters per second, 2.99 into 10 raised to 8 meters per second in vacuum, and it is 2.98 into 10 raised to 8 meters per second in air. Refractive index is the extent of change of direction of light in a given pair of media. The refractive index is a relative value of speed of light in a given pair of media. Thus, to calculate the refractive index, the speed of light in two media is taken. The speed of light in medium 1 is V1 and medium 2 is V2. Therefore, refractive index of medium 2 with respect to medium 1 is n to 1 is equal to speed of light in medium 1 equal to speed of light in medium 2, or n to 1 equal to V1 by V2. Above expression gives the refractive index of medium 2 with respect to medium 1. This is generally denoted by n to 1. Similarly, the refractive index of medium 1 with respect to medium 2 is denoted by n1 to 2. n1 to 2 equal to speed of light in medium 2 by speed of light in medium 1, that is equal to V2 by V1. Absolute refractive index. When one medium is taken as vacuum and speed of light is taken in it, then the refractive index of second medium with respect to vacuum is called absolute refractive index, and it is generally denoted by n2. Thus, n2 equal to speed of light in vacuum by speed of light in given medium. The speed of light in vacuum is slightly faster than in air. Speed of light in air is v, and speed of light in given medium is v. Therefore, refractive index of the given medium, n power to n equal to speed of light in air by speed of light in given medium, that is equal to c by v. Since refractive index is the relative value of the speed of light of a medium with respect to the speed of light in vacuum, thus light will travel faster in the medium having lower value of refractive index. Optical density. Medium having greater value of refractive index is called optical denser medium. This means light will travel at slower speed in optically denser medium compared to in an optically rarer medium. Spherical lens. Lens is an optical device which converges or diverges the rays of light before transmitting. A lens has similar shape to lenses, and genus of a lens is called lens. Thus, a lens got its name of the shape and name of genus of lenses. A lens is made by combining at least one part of sphere made of transparent material, generally glass. Spherical lens. Most of the lenses are made by the combination of parts of transparent sphere. Concave and convex lens are most commonly used spherical lens. Convex lens is most commonly used lens in our day-to-day life. Convex lens. A lens having two spherical surfaces bulging outwards is called convex lens. It is also known as biconvex lens because of two spherical surfaces bulging outwards. Concave lens. A lens having two spherical surfaces bulging inwards is called concave lens. It is also known as biconcave lens because of two spherical surfaces bulging inwards. Important terms for spherical lens. Centre of curvature. Centre of sphere or part of which a lens is formed is called the centre of curvature of the lens. Since concave and convex lenses are formed by a combination of two parts of spheres, therefore they have two centres of curvature. One centre of curvature is usually denoted by C1 and the second is denoted by C2. Focus. Point at which parallel rays of light converge in a concave lens and parallel rays of light diverge from the point is called the focus or principal focus of the lens. Similar to centers of curvature, convex and concave lenses have two foci. These are represented as f1 and f2. Principal axis. Imaginary line that passes through the centers of curvature of a lens is called principal focus. Optical center. The central point of the lens is called its optical center. A ray passes through optical center of the lens without any deviation. Radius of curvature. The distance between optical center and center of curvature is called the radius of curvature, which is generally denoted by r. Focal length. The distance between optical center and principal focus is called focal length of a lens. Focal length of a lens is half the radius of curvature, that is 2f equal to r or f equal to r by 2. This is the cause that the center of curvature is generally denoted by 2f for a lens instead of c. Refraction through lens. Refraction of parallel ray. A parallel ray converges at focus of a convex lens and diverges from the focus of a concave lens. Refraction of ray passing through the principal focus. A ray passing through principal focus emerges parallel to the principal axis after refraction from a convex lens. A ray passing through the principal focus emerges parallel to the principal axis after diverging from a concave lens. Ray passing through the optical center of lens. Ray passing through the optical center of convex and concave lens emerges in same direction without any deviation. Converging lens or convex lens is known as converging lens because parallel rays converge at its focus. Diverging lens. A concave lens is known as diverging lens because parallel rays appear to diverge from the focus after refraction. Image formation by convex lens. There are 6 possibilities of position of object in the case of convex lens. A. Object at infinity. B. Object beyond center of curvature. C. C. Object at center of curvature. C. D. Object between center of curvature C and principal focus F. E. Object at principal focus F. F. Object between principal focus F and optical center O. Object at infinity. Convex lens converge parallel rays coming from object at infinity, and a highly diminished point size real and inverted image is formed at principal focus F2. Properties of image. Image is highly diminished, real and inverted. Object beyond center of curvature C1 or 2F1. A diminished, real and inverted image is formed between principal focus F2 and center of curvature C2 on the opposite side, where an object is placed beyond C1 of a convex lens. Properties of image. Image is diminished, real and inverted. Object at center of curvature C1 or 2F1. A same size, real and inverted image is formed at center of curvature C2 when object is placed at center of curvature C1 of a convex lens. Properties of image. Image is same size as that of the object, real and inverted. Object between center of curvature C1 and principal focus F1. An enlarged, real and inverted image is formed beyond center of curvature C2 when an object is placed between center of curvature C1 and principal focus F1 of a convex lens. Properties of image. Image is enlarged, real and inverted. Object at principal focus F1. An infinitely large, real and inverted image is formed at infinity when object is placed at principal focus F1 of a convex lens. Properties of image. Image is highly enlarged, real and inverted. Between principal focus F1 and optical center O, a virtual erect and enlarged image is formed at the same side of lens when an object is placed between principal focus F1 and optical center O of a convex lens. Properties of image. Image is enlarged, virtual and erect. Image formation by concave lens. There are only 2 possibilities of position of object in the case of concave lens. A. Object is at infinity. B. Object is between optical center O and infinity. Object is at infinity. A highly diminished point size, virtual and erect image is formed when object is at infinity by a concave lens at principal focus F1. Properties of image. Image is point size, highly diminished between optical center O and infinity. A diminished virtual and erect image is formed between principal focus F1 and optical center O when object is placed between optical center and infinity of the concave lens. Properties of image. Image is diminished, virtual and erect. Sign convention for lens. Sign convention for lens is similar to that of spherical mirror. Signs are taken left of the optical center as negative, right of the optical center as positive. Above all, the principal axis as positive and below of the principal axis as negative. The new sign convention is known as new Cartesian sign convention. In this, sign is taken negative towards left and taken as positive towards right at x-axis from origin. The sign is taken as positive plus above the origin point at y-axis and below the origin point as negative minus at y-axis. Lens formula and magnification. The relation between distance of object, distance of image and focal length for a lens is called lens formula. 1 by v minus 1 by u equal to 1 by f, where v is the distance of image, u is the distance of object, and f is the focal length of lens. Distance of object and image is measured from the optical center of the lens. The sign for distance is given as per convention. The lens formula is valid for all situations for spherical lens. By knowing any of the two, the third can be calculated. Magnification. The ratio of height of image and that of object, or ratio of distance of image and distance of object, gives magnification. It is generally denoted by m. M equal to height of image h dash by height of object h. That is equal to distance of image v by distance of object u. The positive sign of magnification shows that image is erect and virtual, while the negative sign of magnification shows that image is real and inverted. Power of lens. A convex lens with short focal length converges the light rays with greater degree nearer to principal focus, and a concave lens with short focal length diverges the light rays with greater degree nearer to principal focus. The degree of divergence or convergence of ray of light by lens is expressed in terms of the power of lens. Degree of convergence and divergence depends upon the focal length of a lens. The power of a lens is denoted by P. The power of a lens is reciprocally the focal length. Power P equal to 1 by focal length F, or P equal to 1 by F. The SI unit of power of lens is diopter, and it is denoted by D. Power of a lens is expressed in diopter when focal length is expressed in meter. Thus, a lens having 1 meter of focal length has power equal to 1 diopter. Therefore, 1 is equal to 1 m raised to minus 1. A convex lens has power in positive and a concave lens has power in negative. Power of optical instruments having multiple lenses. There is more than one lens here. The total power of lenses is equal to the sum of power of all individual lenses. For example, if there are 3 lenses used in an optical device having powers equal to 1D, 2D and 3D respectively, therefore the total power of the optical device is equal to 1D plus 2D plus 3D equal to 6D. Some common phenomena of refraction. Bending of pencil when placed in a glass with water. When a pencil or stick is kept in a beaker or a glass filled with water, the stick appears slightly bent. This happens because the light entering from air, rarer medium, into water, denser medium, bend towards normal to the incident, which makes the appearance of pencil or stick as bent. Position of fish in the water pond. The ray coming from fish in the pond bends away from the normal to the incident. We see the emergent ray which makes the appearance of fish slightly above its position. Formation of rainbow. Rainbow is formed just after the rain. When ray of light travels from droplets of rain, it is scattered into its constituent 7 colors and forms a rainbow in the sky. Visibility of sun slightly before the time of sunrise. When the rays coming from the sun enter into the atmosphere, which is denser medium than vacuum, they bend away from normal to the incidence because of refraction. Since we see the refracted rays coming from the sun, that's why the sun becomes visible slightly ahead of the time of sunrise.
Okay, this completes the chapter, and there is the last chapter. The human eye and the colorful world. This will be the last chapter in physics related to 10th standard. today you all gone through complete physics.
The human eye and the colorful world. Introduction. We can see many things around us due to eye. It is wonderful sense organ. It enables us to see colors around us. Beauty of nature with different colors is an eye-pleasing view. Different colored flowers, trees, hills, and ever-changing skyline makes our vision delightful. Human eye is like a camera. Light enters the eyes through cornea. Crystalline lens system helps to focus on objects which are at different distances to form an image on retina. It helps to visualize the objects as they are through light-sensitive cells and their interpretation at brain. Structure of human eye. Human eye is a spherical structure which fits in the eye socket in the skull bone. There are the following main parts in the human eye. 1. Cornea. It is the first part of the eye. It is the transparent window that bulges outwards. It is responsible for maximum reflection of light that enters the eye. 2. Pupil. Pupil is the round black spot in front of the eye. It regulates the amount of light entering the eyes. Pupil works like a aperture of a camera. In case of dim light, pupil dilate to allow more light to enter the eyes. In case of strong light, pupil constrict, allowing less light to enter. Clear watery fluid fills the gap between cornea and iris. The iris. It is the colored part of the eye. Iris is made of muscles. To control the size of opening of pupil. 4. Lens. Lens lies just behind the pupil. It is made up of jelly-type transparent materials. Lens become thin to increase its focal length. This enables us to see distant objects clearly. Focus on nearer objects. Lens becomes thick to decrease its focal length. There is a limit. Minimum distance of clear vision is 25 cm. Below this distance, we cannot see things clearly. 5. Retina. Retina works like a screen or camera film. Retina is full of light and color-sensitive cells. These cells, upon receiving image, send electrical signals to the brain, which processes these information to make a mental image of what we see. Photoreceptor cells in the eye are two types, namely rod cells and cone cells. Rod cells are sensitive to dim light. The cone cells are sensitive to bright light and color. 6. Ciliary muscles. They surround the lens. Shape of the lens is determined by them. They help in adjusting the focal length of the lens by contraction or relaxation. 7. Eyelids. Protect the eye from dust and other foreign particles. Working of eye. Basic operation is similar to a camera. Light enters the eyeball through transparent layer of tissue at the front of the eye called cornea. Cornea bends the light rays through the pupil. Adjusted light passes through the natural crystalline lens. As the eye lens is convex in nature, the resulting image is real, small, and inverted. It is formed on retina. Retina converts these light rays into electrical signals. They are relayed to brain through optic nerve. Brain processes the information and then we can see the object. Benefits of two eyes. One eye is having a field of vision of about 150 degrees. Both the eyes enables us to see up to a field of 180 degrees. Moreover, as two different images gets juxtaposed in the brain, so we are able to see a three-dimensional view of the world. Iris and pupil. Like a camera, shutter controls the amount of light entering it. In the eye, iris and pupil control the same way. Iris contains muscles that allows the pupil to become large and small. Iris regulates the amount of light entering the eye through pupil opening. If the amount of light incident on the eye is high, then the iris contracts, thereby reducing the size of the pupil. This will reduce the intensity of light entering the eye, thus protecting the eye. If the amount of light is low, iris widens and pupil dilates to allow sufficient amount of light, thereby enabling to view image clearly. When we enter a room after a certain duration of exposure to sun, we hardly see things. This is due to the adjustment required to be done by the iris and pupil. Power of accommodation of human eye. The human eye can clearly see a nearby object as well as far distant placed objects. This ability of the human eye is called the power of accommodation of human eye. Here, the rays of light traveling from nearby objects tend to travel differently to the rays of objects from far off distance. Nearby object rays tend to be spreading out, that is, diverging. As a result, they need a lot of bending to bring them to focus on retina. Far distant object rays travel almost parallel. They need less bending to focus on retina. To make this happen, focal length of the eye changes as the distance of the object changes. We know that 1 by v minus 1 by u equal to 1 by f. In case of human eye, the image forming distance is almost 2.3 cm, that is, distance between eye lens and retina. The focal length changes based on the distance of the object. Ciliary muscles contract or relax in response to the light entering the eye. Light from distant objects. The ciliary muscles relax, the suspensory ligaments are pulled tight, and this in turn pulls the lens long, thin, and relatively flat. This is the original shape of the lens. Light from close objects. As objects come close to the eye, the ciliary muscles contract, the suspensory ligaments go slack, and the lens becomes fatter and shorter. This changes the focal length. Power of accommodation is the power of the eye to change its focal length so that it can see both near and distant objects. If an object comes too close to the eye, we may not be able to see it clearly. Object has to be at a distance of 25 centimeters to infinity. This varies with age. For a normal person, anything less than 25 centimeters, object will be seen as blurred. Defects of eyes and correction. A normal eye can see objects over a range of distances, that is 25 centimeters to infinity. But due to certain abnormalities, eyes are not able to see objects clearly over a range of distances, and such eye is said to be defective. Some of the defects of vision are myopia or short-sightedness or nearsightedness, hypermetropia or long-sightedness, presbyopia, cataract, myopia. Myopia is also known as nearsightedness. A person with myopia can see nearby objects clearly but cannot see distant objects distinctly. In a myopic eye, the image of a distant object is formed in front of the retina and not of the retina itself. This defect may arise due to A. Excessive curvature of the eye lens, or B. Elongation of the eyeball. Correction of myopia. This defect can be corrected by using a concave lens of suitable power. A concave lens of suitable power will bring the image back onto the retina, and thus the defect is corrected. Hypermetropia. Hypermetropia is also known as farsightedness. A person with hypermetropia can see distant objects clearly but cannot see nearby objects distinctly. The near point for the person is farther away from the normal near point 25 cm. Such a person has to keep a reading material much beyond 25 cm from the eye for comfortable reading. This is because the light rays from a nearby object are focused at a point behind the retina. This defect arises either because A. The focal length of the eye lens is too long, or B. The eyeball has become too small. Correction of hypermetropia. This defect can be corrected by using a convex lens of appropriate power. Eyeglasses with converging lenses provide the additional focusing power required for forming the image on the retina. Presbyopia. The power of accommodation of the eye usually decreases with aging. For most people, the near point gradually recedes away. They find it difficult to see nearby objects comfortably and distinctly without corrective eyeglasses. This defect is called presbyopia. It arises due to the gradual weakening of the ciliary muscles and diminishing flexibility of the eyelids. Sometimes, a person may suffer from both myopia and hypermetropia. Such people often require bifocal lenses. A common type of bifocal lenses consists of both concave and convex lenses. The upper portion consists of a concave lens. It facilitates distant vision. The lower part is a convex lens. It facilitates near vision. Cataract. In old age, crystalline lens for some people becomes milky and cloudy. This reduces the vision in old age. Cataract can be cured by eye surgery. Sometimes, artificial lens is also transplanted during cataract surgery. This is called intraocular lens transplantation. Refraction of light through a prism. Prism is a transparent optical element which refracts light. An optical object to be defined as prism must have at least two faces with an angle between them. Triangular prism is the most common type of prism. It has two triangular bases and three rectangular lateral surfaces. Angle between two lateral surfaces is called angle of the prism. The process of bending of light ray when it enters from one medium to another is called refraction. When a ray of light enters the prism, it bends towards the normal because light is entering from a rarer medium, air, to a denser medium, glass. Similarly, when the light emerges from the prism, denser medium, it follows the laws of refraction of light and bends away from the normal. Any object that has lower refractive index is called rarer medium. Any object that has higher refractive index is called denser medium. We can observe that a ray of light PE in bends away from the normal. The angle the emergent ray makes with the normal is called the angle of emergence. Extend the incident ray to meet emergent ray at G. The angle between these two is called angle of deviation, angle D. Differences in refraction of light through glass slab and glass prism. A glass slab has parallel refracting surfaces, whereas a prism has inclined surfaces. In a glass slab, the incident ray and emergent ray are parallel to each other, whereas in a prism, they make an angle of deviation. Dispersion of light. Sir Isaac Newton proved that white light consists of 7 colors. This was done when the sunlight or white light was passed through a prism. When a beam of white light entered the spectrum, it split into band of colors called spectrum. This phenomena is called dispersion of light. Spectrum of light has Wood-Bury colors, that is, violet, indigo, blue, green, yellow, orange, and red. Splitting of light into 7 different colors when passed through a medium is called dispersion. Due to the angle of the prism and due to different wavelengths of different components of white light, the emergent ray gets segregated into different colors. Anyway, a colorful band of 7 colors is obtained. This phenomenon is called dispersion of white light by the prism. It bends the least and violet bends the most. Thus, the rays of each color emerge along different paths and become distinct. Newton conducted one more experiment. He passed the spectrum of light through another prism. and then he got white light. This observation made him to conclude that sunlight or white light consists of 7 colors. Recombination of 7 colors is called recomposition of light. Applications of dispersion of light. Formation of rainbow. Rainbows are generally formed after the rain. It is concentric colored circular arc in the sky when the sun rays falls on drops after or during a shower. Raindrops which remain suspended after the rainwork like a prism. White light enters a raindrop, it experiences refraction and dispersion. When different colors of light fall on back inner surface of water drop, it reflects them internally. Total internal reflection. Water drop finally refracts different colors of light again when it comes out of a raindrop. As a result, rainbow is formed against the backdrop of sky. Rainbow is formed opposite to the sun. Raindrops act like prism. Rainbow is an example of natural dispersion. Atmospheric refraction. When light enters from one medium to another, there is a deviation in its path. This phenomenon is called refraction of light. Atmosphere is composed of layers of various optical densities. Because of this, light rays passing through various layers of atmosphere get deviated. Many interesting phenomena can be observed because of atmospheric refraction. Air is hot during summer and cold during winter. Fraction in air is dependent on temperature of air. The apparent position of the star is slightly different from its actual position. Star appears slightly higher above than its actual position when viewed near the horizon. However, this apparent position of the star is not stationary but keeps on changing slightly since the physical conditions of the Earth's atmosphere are not stationary. Since the stars are very distant, they approximate point-sized sources of light. The path of rays of light coming from the star goes on varying slightly. Apparent position of the star fluctuates and the amount of starlight entering the eye flickers. That is, the star sometimes appears brighter and at some other time fainter, which gives the twinkling effect. Advanced sunrise and delayed sunset. The sun is visible to us about 2 minutes before the actual sunrise and about 2 minutes after the actual sunset because of atmospheric refraction. By actual sunrise, we mean the actual crossing of the horizon by the sun. The time difference between actual sunset and the apparent sunset is about 2 minutes. The apparent flattening of the sun's disk at sunrise and sunset is also due to the same phenomenon. Scattering of light. When light hits a particle, it scatters in different directions. Refraction happens because of non-uniformities of particles of a medium. Many interesting phenomena can be observed because of scattering of light. Some of them are given here. Tyndall effect. The optical effect because a scattering of light from the particles of colloid or suspension is called Tyndall effect. For Tyndall effect to be possible, the size of particles should be less than or equal to the wavelength of the visible spectrum. So, the size of particles should be between 40 and 900 nanometer. Tyndall effect is responsible for many natural phenomena. The white beam of light which appears to come through the ventilation or through a slit in the door is because of Tyndall effect, and the dust particles in the air cause the scattering of light in this case. The white beam appears because scattering of light makes the dust particles visible in the light. Tyndall discovered that when white light is passed through clear liquid, having suspended particles in it, blue color of white light having shorter wavelength is scattered much more than the red color. Practical use of pinhole effect. Why is the color of the clear sky blue? We know that the wavelength of red color is more than that of blue color. The size of particles in the air is smaller than the wavelength of visible light. Hence, these particles scatter the light of shorter wavelength more effectively than light of longer wavelength. The blue end of visible spectrum has shorter wavelength than the red end. Due to this, blue color is scattered more strongly in the atmosphere compared to the red color. This is the reason sky appears blue. Since red color is scattered the least, hence it is used in traffic lights for showing the danger signal. Water in deep seas appears blue because of this scattering of light.
this will be the end session. This completes the complete physics chapters related to the 10th standard from first lesson to the second sem, the last chapter. So please go through the chapters repeatedly until you understand the concepts. Okay, note down the very important points. Thanks for your visit and watching. Thank you one and all.